Good morning everyone. My name is Mahesh Rame, PRN 125 B1F168. Today I am presenting this topic under the guidance of Dr. Shweta Devdas ma'am. As a first year engineering students, you are probably very familiar with writing simple codes. You know that computers process everything in binary ones and zeros. But have you ever stopped to wonder how a 1 or a 0 actually travels from your laptop through a physical wire and to a server on the other side of the world? A copper wire doesn't understand numbers, it only understands electricity. Today, we are going to explore the fascinating bridge between computer software and physical hardware. This topic is called as advanced digital to digital conversion, and it is the obsolete foundation of the data communication. Let's start by looking at the big picture, the communication system architecture. When you send a WhatsApp message, three major things happens at the physical layer. First, the source encoder. This takes your text message and compresses it into a raw stream of binary bits. Second, we have a line encoder. This is the star of our presentation today. The line encoder takes those abstract binary bits and maps them onto actual electrical voltages and light pulses. Finally, those pulses travel through the light channel, which could be a twisted pair copper cable, a fiber optic strand, or even the air via Wi-Fi. Our focus today is purely on line encoding, the art of turning math into physics. To design a good communication system, we need to understand the metrics we are measuring. Let's use an analogy. Think of bitrate as the number of passengers trying to reach a destination every second. It's our actual data speed. 1 gigabit per second means 1 billion bits are flowing. Now, think of baud rate as the number of buses we use to carry those passengers. Baud rate is the number of times the actual electrical signal changes state per second. In engineering, bandwidth is expensive. Our goal is to pack as many passengers into as few buses as possible to save bandwidth. We also have to watch out for the DC component. If we only send positive voltages, the average voltage builds up over time. These direct current components can fry transformers in telephone lines. We need our signals to average out to 0 volt. You might be thinking, why is this a whole subject? Why not just make 5 volts a 1 and 0 volts a 0? Because the real world is messy. We face two massive physical challenges. First is baseline wandering. The receiver constantly calculates the average voltage to figure out what 0 means. If you send a file that has 10,000 ones in a row, the receiver average voltage shifts upward. Suddenly, it loses its baseline, and it might start reading a real 0 as a 1. Second, and even more critical, is synchronization loss. Imagine I ask you to clap exactly when a clock ticks, but I take the clock away. After a few seconds, you will drift out of the rhythm. Computers do the same thing. If a cable sends a flat plus 5 voltage line for a long time, the receiving computer's internal stopwatch drifts. It won't know if it is just received 50 ones or 51 ones. It needs the signal to transitions to reset its clock. So engineers came together and established 5 golden rules for the perfect encoding scheme. First one is self-synchronization. The signal must go up and down enough times to keep the receiver's clock perfectly in time. Second, minimal bandwidth. It shouldn't require a massive frequency range. Third, noise resistance. It needs to survive electromagnetic interference, like when a power cable is placed too close to our data cable. Fourth one is zero DC component. It must average out to 0 volt to protect our hardware. Fifth is error detection. It would be great if the physical signal itself could tell us if a bit got corrupted. We measure these trade-offs using this R factor. The R factor is the simple ratio bits divided by signal elements. If one electrical pulse carries one bit of data, R equals 1. If we decide to use two electrical pulses to carry just one bit of data, that synchronization problem we talked, our R drops to 1 half, 0.5. A lower R means better synchronization, but it takes up way more bandwidth. A higher R is super fast but very fragile to noise. Let's look at how engineers solve this over decades. First, we tried NRZL, which means non-return to zero level. It's the simplest. High voltage is 1, low voltage is 0. It's cheap, but it fails completely at synchronization if there's a long string of zeros. Then came NRZI, which means invert on ones. Here, a transition means a 1 and no change means a 0. This fixed synchronization for long string of ones, but long strings of zeros still broke the system. So, for local networks like Ethernet, engineers invented Manchester encoding. It is brilliant. It forces a voltage transition in the exact middle of every single bit. A high to low drop is 0 and a low to high drop is a 1 because there is a guaranteed transition every single bit. The receiver's clock never drifts. The catch: it requires double the bandwidth. Finally, we have bipolar AMI, alternate mark inversion. Here a 0 is 0 volts, but for a 1 we alternate. The first one is positive, the next one is negative, the next is positive. This perfectly solves the DC component problem and even provides basic error detection. Manchester was great for early slow Ethernet, but when we moved to fast Ethernet, Manchester's habit of doubling the bandwidth requirement becomes a deal breaker. We couldn't afford it. Enter block coding. Instead of messing with the electrical pulses directly, we add a layer of logic. A famous example of 4B or 5B. We take 4 bits of user data and map them to 5-bit code. Why? Because of those 32 combinations. We can throw away the ones that have too many consecutive zeros. We only use the 5 codes that guarantee enough transitions for the receiver's clock. This gives us synchronization of Manchester, but with only 25% bandwidth overhead instead of 100% overhead. It was massive breakthrough. But what about the long distance telecom networks connecting entire cities? Over hundreds of kilometers, even a 25% bandwidth overhead is too expensive. We need 100% efficiency, but we still need synchronization. The solution is scrambling. We use the bipolar AMI code we talked about earlier, but we add a trick. In North America, we use B8ZS, which means bipolar with 8-0 substitution. If the hardware detects 8 zeros in a row coming from the computer, it doesn't send a flat line. It instantly ejects a fake deliberate signal error, a specific pattern of voltages. The receiver sees this exact error pattern and says, "This isn't a glitch. This is the secret code for 8 zeros," and convert it back. Europe uses the similar system called HDB3, which substitutes every 4 zeros. Scrambling gives us perfect synchronization with zero wasted bandwidth. As you move through your engineering degree, you will hear the phrase "no free lunch." That applies here. Block coding gives you guaranteed transitions and required very simple hardware, but we pay for it by losing our 25% of our bandwidth. Scrambling is 100% bandwidth efficient and solves the DC problem, but it requires much more complex hardware logic to constantly scan for long strings of zeros and replace them on the fly. You might think this is just a textbook theory, but you use this constantly. When you plug in an Ethernet cable in the computer lab, you are using Manchester or 4B or 5B block coding. When you plug a pen drive into your laptop, the USB 2.0 protocol relies on NRZI combined with a technique called bit stuffing. And when you make a mobile phone call, the massive cell towers routing your voice to the main network use B8ZS and HDB3 scrambling. To conclude, digital to digital conversion is where the abstract world of computer science shakes hand with the physical laws of electronics. By carefully selecting between line coding, block coding, and scrambling, engineers have managed to build the incredibly fast, reliable internet we rely on today. You can refer these books to grasp more information about this topic. Thank you very much for your time and attention. I would now like to open the floor to any questions.